Hello everyone. Today I'll be presenting our exploratory study that investigates how augmented reality can be used to design adaptive motor skill training tools by adjusting the functional task difficulty. Skill learning is an integral aspect of our development, and we learn physical or motor skills all our lives. Whether it is learning the pincer grip in infancy, which is a significant milestone in cognitive development, or learning biking or basketball for sports and recreation, all the way to exercising for health and muscle rehabilitation, we are constantly learning to perfect motor skills. And among several ways in which we learn motor skills, my formative interviews with coaches revealed that they use the approach of adaptive learning, where the functional task difficulty, that is, the difficulty experienced by the learner, is adapted by the coaches or the trainers. And they do this so that the training difficulty is maintained at an optimal challenge point, that is, the training task is neither too hard nor too easy for the learner's skill levels, because that's when the potential for learning is maximum, which is what we want to capitalize on. But not everyone has access to well-trained personal coaches and trainers, so how do we make this adaptive learning accessible to a wider group? Some of the prior work addresses this open question through an approach where instead of the trainers adapting the difficulty, the tool itself can sense the skill levels and adapt itself to change the training difficulty. For example, in this prototype of adaptive basketball hoop, the sensors on the stand measure the learner's performance, and then based on that, adapt the hoop width accordingly, as well as adapt the hoop height to increase the functional task difficulty. The goal of the approach here is to take the learner from being a novice to being an expert, all while maintaining the functional task difficulty at an optimal challenge point. This approach of adapting the functional task difficulty has been implemented to design several adaptive physical training tools. For example, an adaptive skateboard that changes its length based on the learner's balancing skills, or adaptive gloves for learning sign language that provide more or less support as the learner gets better. Despite the generalizability of this approach, adapting physical tools can have several limitations. For example, the adaptation can be slow. You need a physical tool to adapt and are limited by its mobility, and the tool is typically designed for a single function. But in contrast, virtual tools like augmented reality environments can have the benefit of fast or instantaneous adaptation. You're not bound by the physical tools and its mobility, and the device can be used for multiple purposes without much updates. We explore this potential of AR environments through our work on investigating the design of adaptive AR training tools. In particular, we explore and extend the design space of adaptive tools, where if we were to map the motor skills for physical to virtual environments on one axis and physical to virtual training tools on another axis, we focus on the design of adaptive virtual AR learning tools for motor skills used in the physical environments alone. And while the current related work in this space focuses on providing feedback on performance, instructions on how to perform the task, and even overlaying information during the task performance, there is no prior work on investigating how to adapt the functional task difficulty in AR. We address this gap with two research goals. First is to study how the learning gains and experiences of training with adaptive AR differ from non-adaptive training. And second is to understand additional design challenges that arise with adapting functional task difficulty in AR as compared to the physical training tools. We addressed these research goals through the following contributions. First, we conducted a between subjects exploratory study on training using an adaptive AR tool. And second, we conducted a thematic analysis of the participant feedback to identify the design challenges and opportunities for adapting the task difficulty in AR. For the exploratory study, we chose the motor skill of throwing a ball into a ring, which is not only inspired by prior work, but also a widely studied skill in the motor skill literature. For the training conditions using AR, the participants trained to throw a physical ball inside a virtual hoop seen through a HoloLens headset with a ring that was located at a fixed distance and height from the participants. To track the position of the physical ball, we used OptiTrack cameras, seen here in this video of the study setup, and while you see that the learner is aiming at the physical ring in this video, we built an exact replica of the ring in AR. Here is how it is seen through the HoloLens. We changed the color of the ring based on the attempt score. If the attempt was successful, the ring changed to green. If the ball completely missed the ring, then the ring changed to red. And if the ball hit the rim, then the ring changed to yellow. Here is a demo of the non-AR, that is the physical condition, seen from the learner's perspective. As you can see, the learner is throwing a physical ball inside the physical ring. And here is a demo of the AR condition, adaptive and non-adaptive, also seen from the learner's perspective through the HoloLens. And as you can see, the learner is throwing a physical ball inside the virtual ring seen in AR. We evaluated the participants' performance in real time, and based on their score, our algorithm assessed if the current training difficulty was optimal or suboptimal. The algorithm for adaptation was modified from the prior work on maintaining optimal challenge point. This between-subject study was about 60 minutes long. The participants were first assigned one of the two groups, Group A, where they were trained on non-adaptive AR training, and Group B was trained on adaptive AR training. Both the groups had the non-AR training or the physical training as their control condition. Within these two groups, the participants were randomly assigned the control or the training condition first to counter the order effect. And for each of the training conditions, the participants attempted 60 throws. Note that the pre-training and the post-training tests were always conducted on the physical non-AR condition for 20 attempts. The difference between the pre- and the post-training test scores were calculated to assess the learning gains. Altogether, we tested with 16 participants between the ages of 25 to 63, all of whom had prior experience with AR and VR environments. For our results, as expected, the learning gains in the adaptive condition were slightly higher than the other two conditions, although the difference was not statistically significant. In terms of preference, that is, when asked which training would the participants want to continue to train on, there was a slightly higher preference for the adaptive AR condition compared to the non-adaptive AR condition. However, there was a very strong preference for the regular physical condition, even though the learners learned better with the adaptive AR condition. And diving deeper in the data through thematic analysis revealed some very interesting insights, particularly on the design of adaptation. First, the learners found it hard to perceive the adaptation, as when the ring adapted to smaller or larger, the learners perceived it as the ring was getting farther or closer to them. This shows the importance of designing environmental cues such as shadows and occlusions between the physical environmental objects and the virtual objects, particularly those that are adapting in space. Similarly, absence of cues such as noise and vibration that occurs when the ball hits the ring were very crucial in how learners updated their mental state of their own performance and planned the next attempt. Despite the limitations of current technology in sensing such contextual information, capturing the full range of nuanced interactions, and simulating realistic adaptations, we still see design opportunities for adapting functional task difficulty. For example, using AR visualization overlays such as text or visual markers superimposed on environments that can vary the task difficulty during the training for the learners. As AR advances in tracking, sensing, and realism, new opportunities can emerge to adapt functional task difficulty using multimodal cues. Because learners rely on spatial, such as depth distance, sensory, such as visual or auditory, and temporal, such as timing or speed cues for performance, these cues can be dynamically adapted to increase or decrease the perceived difficulty. Finally, as AR technology evolves to be more advanced, designers can manipulate realism to adjust the task difficulty, for instance, by selectively muting specific visual or sensory cues while keeping others constant in order to increase the motor skill expertise while reducing reliance on specific feedback. More speculative approaches might creatively alter the physics of the environment, such as replacing a physical ball with a slow-motion AR visualization post-throw to highlight the trajectory, with the speed adapting as the learner improves. While our exploratory study offered valuable insights into AR-based adaptive training, it also has several limitations. We focused on a specific ball-throwing task, which may limit generalizability, and future work should explore other complex motor skills. A single-session study design also restricts our understanding of long-term learning, underscoring the need for longitudinal studies with more participants. And for future work, we also plan to combine adaptive training task difficulty with instructional and feedback techniques, and believe these strategies could further improve AR-based motor skill learning. In conclusion, this work on investigating the use of AR to adapt functional task difficulty in motor skill training highlights several unique design challenges and opportunities not present in the physical tools and points to new directions for future research in this field. Thank you.